Hello everyone, today I'll be talking about the two coins puzzle. It's a quite interesting puzzle because it can be applied to software, and also you will have the opportunity to return if it's not the first time that you're hearing about it, or maybe you start to learn about the Bayes Theorem. It's a theorem that was invented probably 300 or 400 years ago, but it's applied in a lot of different science, not only in statistics, but also in software, for instance, machine learning, spam filters and things like that. So I will present the puzzle, then I will present the Bayes theorem and some, I won't say theory, but some explanations and intuition and rationale about it. I think it will be a good tool for you to learn it if you don't heard about the Bayes theorem before. Then we'll be checking these 6 use cases regarding ML spam, medical testing, fraud detection, A/B testing, debugging random failures in a system, and machine learning model accuracy. Usually I provide timestamps. Maybe you don't want to hear about the Bayes theorem, you don't like math, you don't like to check formulas. That's okay. Sometimes I'm not on the mood also, but at least you can check, for instance, the puzzle, and then you can jump in the timestamp for use case 1. And if you understood the puzzle and a little bit of the Bayes theorem, you will understand how it can be applied here, because all of these use cases will use the Bayes theorem formula. Maybe you don't understand the formula, but if you know the formula and you can use it, and you only need to understand the parameters of the formula, like a regular formula. So what I'm trying to say, there are 2 or 3, maybe 5 or 10 minutes that you can skip if you don't want to check how the Bayes theorem works and why the theorem is as is, and you can just jump using the timestamps. But I hope you at least follow the use cases, because I think they will be useful for you professionally if you are on the IT industry. Okay, so let's start with the puzzle. So the puzzle, you have 2 coins. That's the puzzle about the coins. You have 1 fair coin, equal chance of heads or tails, and 1 biased coin, more likely to land heads. But you don't know which one is biased and which one is fair. You just have 2 coins in your hand, but you know that one of them probably it's not fair. So you randomly choose one. So you take one of the coins from your hand and you flip it twice, and you have a result which is 2 heads. And the thing is, what is the probability that the coin is biased? And this can be applied in a lot of different scenarios. Sometimes it's just a simple puzzle and say, okay, this is a puzzle, nice, it's a challenge to my mind. No, it's not. Imagine that it's not 2 coins, but there are 2 systems in your architecture. And you know that there are some fails, but you don't know which one. You know, maybe you have an understanding about the number of defects or problems that arise during the day or per week in these 2 systems, but you don't know clearly which one is responsible for what. One of them is biased, the other one is fair, meaning that you understand what is the probability directly of something to happen. But the other one you don't know, but you don't know which of these 2 is responsible or is the biased one, let's say like that. And you can apply this if you check the use case in more scenarios in your daily life and even on the software. Sometimes that's why I like to provide these puzzles, because it starts to be a puzzle, but if you switch the items in the puzzle with real things, you can see that most of the times you start to learn something that if you solve the puzzle, you solve the issue that you have in software. And by the way, if you think for a while, most of the problems that arise when we are developing or architecting a software, they are puzzles to be solved. If you think for a while, you will see that most of the time there are puzzles. And that's why I once in a while I like to provide a video about puzzles that I think fit the architect or the software engineering. They are good fits for that. Okay, that's the better way to say. So let's start the Bayes theorem here. So this is not the regular formula. This is the formula that you can apply using the Bayes theorem. If you go to the internet and check the formula, it's quite simple, and I'll show you how you can reach this formula. This is the formula that you should look for, because at the end of the day, and I don't want to go into much details here, you have a kind of hypothesis saying something like, I think one of the coins is biased. I flip my coin and twice appear heads. So I want to test this. But for you to test something or to reach a conclusion like a detective, you need evidence. And that's what you have here. So the probability of something that you want to prove given something, okay, that's, and you, of course, you need evidence, you need an experience to provide that evidence. So you have to, for instance, in a software industry, you have maybe the number of defects that happens in one system and the other, and say, okay, every 100 hours, one of them fails 60% of the time and the other 30% of the time. And that's evidence that you have. And you want to check what, based on an hypothesis, okay, what is the probability to be the system one failing? And that is the biased one. And then you apply this formula. So you have to have these values, but these values are always, all of them that can be deduced, or they are given or deduced by the hypothesis. And yeah, but you'll see in a moment some examples, and you will see that it's quite simple to find these values because most of the times they are given to you. If you don't have it, maybe it's you cannot apply the Bayes theorem. And you have this an explanation here if you want into more detail. So the probability of the hypothesis given evidence. Here I say probability of an hypothesis after seeing the evidence. It's something that it's after. That's what we want to understand. Now, pH is initial belief in the hypothesis. Sometimes it's just 50-50. For instance, in a coin, it should call it what is your previous knowledge about the coins, a fair coin. Usual for me, a coin, when I flip it, I expect 50% tails, 50% heads. That's what you have as your hypothesis. And then chance of seeing evidence in if the hypothesis is true. It's what you think it's a probability, something that you know about. It's the probability of, let's say, the evidence to let's say to see heads if I know that the coin is biased, for instance. Okay, but you can apply, I will see in a moment some of the examples for this. This is the complement, probability that the hypothesis is false, and chance of seeing the evidence if the hypothesis is false. This is quite simple to check, and you will see in a moment how can we apply this. So if you want, you can pause here if you want to deduce. Usually this is the standard formula. Okay, but step by step, there are some explanation for this you can find on internet. I will not be a teacher of math here. I think it's not what we are looking for in these videos, but there is a step by step that will reach this formula. So if you are used to see this one as base, it is the same as writing like this, and they just use things like sets theory and things like that to deduce. It's a kind of unions and intersections. Okay, and by the way, when you use this formula, this version is often used in real-world applications like spam filters, medical testing, and fraud detection. That's where it's used, and sometimes people, okay, just math. No, it's not, it's more than that. It's great math. The Bayes theorem is quite popular. So what is the intuition behind this theorem? Imagine that you are guessing if a locked box contains gold or rocks. So you have a box, and it can contain gold or rocks. It is as simple as that. So you shake it, you take it and shake it, and you say, this seems heavy. And usually, you know by knowledge that gold boxes usually sound heavy 90%. So you have a good guess, maybe this is gold, but you are not quite certain of that. But you also know that rock boxes sound heavy only 20% of the time. So it can be rocks there. Because sometimes you say, I'm sure that is gold because, yeah, that's how it sounds. But sometimes I'm wrong, and I'm wrong at least 20% of the time. But you have no clue. If you go by facts, the only thing that you know, you have a box and you want to understand what's inside. You want to check what is the probability, for instance, that is gold that it's inside. But at start, the only thing that you know, it's 50-50. You say, it can be gold or it can be rock. But I know by evidence, but you have something prior, which is 50-50. But I know by experience, my evidence, my knowledge, my statistics, my history, the number of defects that I collected during the last month, the number of failures that I monitor on this system, that 90% of the time it's gold and 20% of the time it's rock. That's the difference. It's something that what you expect by default, which is 50-50. You had no clue before, open the box, but you already have some evidence. Things that happen. Like when you have a detective and he has some evidence. You say, okay, who is the killer? There are two people. Okay, 50-50, I don't know. But this guy has blood in the shirt. Usually in 70% of the cases, these guys probably are the murder. Okay, so that's one way to see it. The evidence, you start with the basics, but then you have evidence that change. You want to check after you apply the evidence what will be the probability. Okay, that's what we want to expect from this theorem. So the probability of being gold is 50 and rock 50, because I don't have any information about what's in the box. I just have history and evidence, but my hypothesis is 50-50. But if I use the probabilities by evidence, the probability of being heavy, knowing that it's gold inside, it's 90%. And if it's rock, it's 2. And if you look at this piece, they will fit this formula. You just have to replace them here. Okay, that's why the most important thing to understand how to apply this theorem first is what is the right place to apply it, and then is collect all the information and put the numbers that you have there and correctly, and after that you'll see that you have everything that you need to apply the formula, and this is what you want to calculate. So in this case, applying the Bayes theorem, the probability of being gold, knowing that it's heavy, that's what I'm checking. Is this gold or not? What is the probability to be gold? And then you apply that formula. This is the numbers that you should put there if you follow the formula, and it will give you 81%. Probably you expected this value because 90% it's a lot. Here's 0.9, the relation between heavy and gold, but this is the correct percentage. And these numbers can be really good, not only for a person to understand them, but for a computer system when you want to automate things. Then you can now use these numbers to, for instance, for spam filters. And when you are correct, it was, for instance, an email that was spam. Okay, you can reinforce this experience here, and later when you apply the formula, maybe the value increases. Or maybe you are wrong and you are teaching the system to say, okay, be careful, maybe I will increase this one. So next time, when you check with the same evidence, you will see that it will not be 81, maybe 75 if you are doing a lot of mistakes when you apply the probability. Of course, this is a kind of using the Bayes theorem with some reinforcement learning. Say, okay, you are right, it's really spam, so I will increase this evidence. No, it's not, you are wrong, so you'll increase this one. It's like a punishment, but this punishment will teach our system what are the correct documents or not. It's more than that in machine learning, but I think the rationale, it is this one. And if it's the first time that you are hearing about machine learning and artificial intelligence, or you never study deeply, this is how things work. Of course, the systems like GPT, it's so much more complex, but this is one of the tools. And Bayes theorem, I can assure you, it's everywhere. So step-by-step solution to the puzzle, if you want to follow. Okay, you have, let's say that B, choose the bias coin, F, it's the fair one, H2, because I will flip twice. So when you flip twice, you have two things that happen in sequence. And usually if they are not related to each other, meaning that the second time you flip the coin is not related to the first one, and it's not because the result of the first one doesn't influence the second one, usually you multiply these properties. That's why in these formulas, usually you square the numbers, because you are multiplying those. Okay, that's why you are putting a H2 here, but you will see on the values, you will square the numbers. That if you want to know more about that, just read the statistics and you will see that how it works. So we want what is the probability of being biased. I'm trying to find which coin it's not the fair one, knowing that I saw 2 times heads. Okay, that's what it means, this H2. And this is the formula, but we have to put here two events that happening. So we square this value. Okay. So if you do the math here, suppose the biased coin lands 90% of the time. Okay, you throw several times and you gather this knowledge, and the fair coin lands at 50% of the time, which is what we expect. Okay, so of course you need evidence about it. You have to throw, let's say, several times and see, okay, now I have a kind of a trend here, a value that I can use. So let the biased coin probability to be this one of happening. This is the, for heads, of course, this is the fair coin is expected 0.5. When you apply the formula, you will see that it will give you 76%, meaning that if you throw or flip the coin twice and you have heads, it's high probably with 76% to be the biased coin. So again, if you change these coins to systems, emails, or other kind of things, you will see that it's a good number for you to say, okay, maybe it is this system, I should check it. It's not 100%, you cannot be sure to say it is this one, but I would start with that one. That's the rationale behind these things. So in the Bayes flow diagram, in a more, let's say, light approach, so you have something that you know about the system, some information. Then you have evidence, you do some experience. Maybe it's the number of defects that appear, something that gives you the probability associated of that happening. There's something that will be the fair one, 50-50. You have 10 systems, 10% each of failing. But then sometimes you start to see that a few of them, they have high probability to fail, and you count this, and these numbers will be these ones that you put here for each one of the systems, and then you apply the formula. Then you have the likelihoods, and then you have the posterior belief. After you calculate, you say, okay, now I believe in this value, this is the correct value. So this process helps us to systematically revise what we believe based on data. And this can be applied to software, even in our daily life. In some things, some of decisions we take, sometimes we don't do this approach because mathematics people run away a lot from them, but it can be applied even in real life things, and you will see some of them. So let's see email spam detection, some use cases here. So you receive an email that contains certain words like urgent, winner, limited offer. When I see these words, in my mind, as I mentioned, it's spam, but I'm not sure. Maybe someone is sending me an email saying urgent. Maybe it's for my company. Maybe I won something. It's very rare. I'm not a lucky person in these kind of things. Limited offer, unless if it's from Amazon or something like that. I never believe it. But okay, this is quite simple to understand. Maybe it's spam, but I have to make sure. And imagine that we already have some percentage, some calculation that we did in some of our documents, or maybe you bought a system that already has some statistics and we want to improve the system in our company or on our software. So from historical data, we can say that 68% of spam mails contains those words. So I have all my emails, you say, I did a count, and all 60% of my emails, all of them contain these words. So there's a high probability to be spam. But sometimes 40%, which is quite a big number of legitimate emails, so sometimes I receive emails that are serious emails with these words. So should I decide this is a spam or not? That's the question. So assume you initially treat any incoming email as equally likely to be spam or not. Again, 50-50, I don't know if it's spam or not. That's what I want to decide. So let I need the evidence, be the event, that an email contains those words. So I receive an email and contains these words. So let's apply Bayes theory. So again, using the formula, I have this 68. This is my prior knowledge, 50 here. You can see these numbers are also, they are all of them taken from here. And then when you apply the formula, you see, okay, there is a 62% probability of being spam. Okay, conclusion, seeing these words boosts the chance the email to spam. A strong enough sum to mark it for review. Maybe you can say, okay, 62%, I'm not sure it is, but it has a high probability. So, okay, let's review it. Maybe send to someone it's like the phishing emails you send to cybersecurity. Maybe you have someone on the company, or maybe the person can look into it and say, maybe your system just put read only on email, so it doesn't harm your system. And then you check the emails and now this is spam. And you mark it as spam, so you can increase now this 68. So you are teaching the system. But if you mark, no, it's not spam, so we will change this one. And the next email that you will receive to be analyzed by spam, these numbers will be different and we will calculate it. And you hope that at some point, that when an email is real spam, you expect for this probability to be very high and say, okay, I can be right maybe 90% of the time. So I will allow the system to automate these emails without asking me. If this value reaches something like 90%, I want to move it to the box, call it spam, and someone looked into it and it can decide to remove it or not. Okay, that's one way to apply the Bayes theorem here. So let's say medical testing, and you now understand why in some medics, some doctors take some specific decisions. So you are a doctor reviewing a patient who has taken a diagnostic test for a rare disease. So someone did a test and say, okay, it seems that you have a rare disease there. It's strange, at least it seems that you have. So the patient tested positive twice in a row. It's like the coin being thrown twice. Okay, naturally, the patient is worried and wants to understand how likely is that they truly have the disease. You want to check, okay, what is the probability of me being really have the disease? So no information. Only 5% of general population has disease. It's something that should be given to you. It's the evidence again. And the test has 85% true positive rate. It correctly detects disease, meaning that when the doctor said that the person has the disease, he is right 85% of the time. But there are also 1/3 of the times is wrong. Okay, and usually only 5% of the population has this. So the probability of someone has this disease is 0.05. It's like when you have a fair coin, it's not fair, but one of the coins, when you throw it, it has 95% of a pair and the other 0.05. It's the same concept as the coin, but now with different values. And that's why you see here 0.05 and here 0.95. If you go to the formula, you will see if you check the formula applying the coins, you will see it's the same formula, but here you use different values. And of course, this is square because I did the test twice in a row. I went to 2 doctors. That's why it's always a good idea to have a second opinion. And both doctors say, okay, it was positive. And hey, it's really strong, but let me do the calculation. And it says that it's 30%. That's the probability for me to have a disease given these values, this evidence. So conclusion, even after 2 positive results, there is still a 70% chance the person is actually healthy. Even if 2 doctors say that I have the disease. This is why doctors use multiple types of evidence, symptoms, history, and more tests before confirming a diagnosis. Because even 2 doctors believing 80% of the time that they are right, even that the math says that, okay, they are only 30% right. Okay, because the probability for really have a disease, taking into account that only a very small part of the population has that disease, it's very low. Now let's see fraud detection. Imagine via bank, it's the same concept. Again, you are monitoring user behavior in a banking system. Most users are legitimate, but a small fraction might be fraudsters. Okay, you have an alert system that flags suspicious behavior. Again, you have a system that flags a suspicious mail. You have a doctor that finds someone probably that has a disease. You find that probably one of the coins is biased. It's always the same concept. You are only changing the entities. So a user just triggered 2 frauds alerts in a row. The toss was coined twice. I saw 2 doctors. Okay, and you want to know how likely is it that this user is actually a fraudster. Now you need evidence. So 1% of users are fraudsters. That's what you have. From the history, you say, okay, usually in 1,000 users, only 10 usually are fraudsters. But frauders triggers the alert 80% of the time, and legit users, sometimes it happens, the system thinks they are fraudsters, but they are not, happens 35% of the time. You can see there is a lot of similarity with the medical testing. It's the same. So it's not a person now, it's just someone trying to fraud the bank. So let A be the event of 2 independent fraud alerts that you receive. You apply the Bayes theory and you receive a 5% chance of being really a tentative of fraud on the bank. So conclusion, even though, now you have to take the conclusion, 5% seems low, but it's too much. Why? Because you expect to be not more than 1%. Usually it's 1% of probability to be a fraud. And if the formula gives you 5%, you should see what's happening. That's one way to apply it. This is numbers that we use based on the context of the problem, of course. So imagine that you have A/B testing. I don't know if you know what is A/B testing in a software. It's when you imagine that you have a website and you say, I want to migrate this to a new different site. For instance, ChatGPT sometimes has these things. It gives you 2 answers and asks you, which one do you like more? It's an A/B testing. That's what it's doing. So it can decide if it should go with the current option or maybe it can improve or not. Okay. So you're running an experiment, 2 different landing page designs, meaning that sometimes you give and you can do a percentage, maybe 50-50, or maybe you take a kind of a random thing and you say, for each 10 requests, one of them I'll send the user to one specific page, or maybe you already choose the users that should go to specific page. Maybe they are in a specific country. It depends on the context or the application. But you want to check what is the most used or people like more of the landing pages. So we have a version A and a version B to see which one converts better. So meaning leads users to take the desired action. Meaning that you will present 2 pages and you say, okay, the people I arrived to this page, and then it followed from this page. It didn't and went back. It didn't stop here. It didn't leave the site. It was just click it and continue, and so it converted the action that he was his purpose on the site. Okay, so for previous data, version 8 typically converts 64% of visitors. Remember, it's like the spam. Again, it's the same concept. So I receive an email and I want to check if it's spam or not. I receive the version A page, and usually I go to people will keep here 64% of the time. Version B converts 47% of the time. You run an early test where 2 users visit one of the pages. So you arrange a way to make the 2 users in a row go, for instance, to a specific page and want to check the probability of that. It's the same concept as the coin, same concept as the medical, always the same way of thinking. And both convert. See, okay, it's like 2 heads of the coin. Let E be the event that both users converted. So the probability of the page A to be a page A that it was converted is 65%. Okay, conclusion, even with very little data, Bayesian analysis gives you an early indication that version A is more likely to be better performing option. That's what you can conclude with just this formula. Intuitively, we already know more or less that, but this is quite strong because it's on the same, let's say, percentage that you expect for this version A. Okay. Of course, in future experience, this can revert. Doesn't take this, okay, so I will choose A. That's not the approach. Maybe you want to do more experience, again with 2 users, and check if this one increase or this one increase, and then you recalculate this and make sure that you are right or not. It's this Bayes system is really good when you try to learn from it or teach a system how to behave, for instance. So use case 5, debugging random failures. So you are investigating an unstable application that recently experienced 2 consecutive backend failures. Again, 2 flips of a coin, and so on and so on. The app depends on 2 services, A and B, and you are trying to figure out which one is more likely to be at fault. So you have 2 systems, you don't know which one is failing, but you know that is one of the 2. So you have some history, so you have evidence that say the service A fails 70% of the time, service B fails 45% of the time. If you return here, version I typically converts 64% of the time, version B converts 45%. I think at this time you already see the pattern. So let it be the event that 2 errors are observed, apply Bayes 70% for the A. Okay, this is quite similar. It's a coincidence, sometimes it's not. If you remember our previous exercise, it was not these numbers because we are using the 70 for 40 here also, so the formula will reach very similar values. But if this number is completely different, or this one, and we're not in this range, the number will not fit neither 70 neither 45. So conclusion, the evidence suggests that service A is more likely culprit behind the failures. This gives you a rational starting point for prioritizing or debugging efforts. That's one way for you to decide, and you can automate this kind of calculation. If you have a system that collects metrics, just take them, put the formula, and okay, let's start with this one. Sometimes people are in the meeting, should you start with this one or this one? And then they discuss for, I don't know, the time it takes, the stop, the start, the customers, and so on. So someone gives a formula, say, okay, this formula is saying that we should start with A. It's high probably, which is a good thing, because if we start with that one and it was this one, so our system will be fixed. Okay, and you have concrete math trying to prove your case. Let's say like this. Machine learning model accuracy, it's really used the Bayes Theorem. You're comparing 2 machine learning models, again, trained to classify whether a customer will buy a product. And I work in a bank that we had a system like that. And it was about credits in a bank, and even could guess what will be the best rate to ask for the customer. So evaluate their performance by checking how often they make correct predictions. And model A is known to be 79% accurate, so they can guess if the model A can guess if the customer will buy the product or not. And model B can reach 51%. You run two predictions is one of the models, and both predictions turn out to be correct. So you run two predictions, say, when I do this for this customer, I'm sure that he'll go to this product, and one will be for this product. That's what you're trying to guess. And when that happens, you say, okay, it seems that the system is working. So let A be the event of two consecutive correct predictions, apply Bayes, and you can say that A is most accurate with this probability. It's not that it's best to this one. In this case, with these numbers, 70% of the time, it's better. That's what he said. It's not 79. Intuitively, from the human point of view, we always think, okay, this is accurate almost 80%. That's it. No, it's not. It depends, because when we are testing with two consecutive, what if it was 3? What if it was 4? And then it's completely different. The values can change. It depends on what we want to test. Okay, take the rationale behind this as some information that you receive that will help your system to evolve and for you to take decisions, not final decisions. Okay, it's not that it's important. And usually, as I usually explain in my architecture videos, if you are following them, it's all about trade-off, good decisions, high probability. There is no right answer. There is no such thing. And you are a great senior, a great architect when you start to think in those terms. You have the metrics, you have a lot of tools like this one, decision frameworks, things like that. You say, okay, from these values, I would say that the evidence shows me that I should start from here and we should try this first. And then we check the other options. That's the approach. It's not, I believe this is the right choice because 80% of the companies they use. Yeah, but my company, it's not the other companies. They are not the same people, the same money, the same geography, the same customers. Nothing is similar. So it's not a reason. It's just an opinion, okay? And hoping a lot. Conclusion, early performance suggests the model is more likely to be one in use. While sample size is small, it's good early indicator of higher accuracy. It's intuitively from the values, and probably this is the reason from previous executions that make this value grow here. So final takeaway, Bayesian reasoning isn't just for puzzles. As you can see, it's powerful mindset. And again, I think I really like this sentence. It's a powerful mindset, the way you think about the problems. Start with prior knowledge, because it takes the prior knowledge that you already have. You add some real world evidence, something that can change the probability, something that can challenge your prior knowledge and update what you believe. So now you think on the system differently after you get these values. You have a current state, a context in your mind. Say, I think that this is the best one. I should start with this one or this one. So let's do an experience. Let's run these 2 or 3 times. Now apply the formula. Maybe I was wrong. That's the way of the Bayesian reasoning. Doctors, engineers, analysts, everyone can benefit, as I show you in several examples. So thank you for learning. Thank you for watching this video. I was really thinking to not publish this video because it's a lot of math. People run away from that. But I think it can benefit you. I think it can teach you about how to look at the things and not quit them at first or make assumptions without really doing experience and take real data. And I think it allows you to get real data to show when it's necessary. And I think that's why I publish it anyway. I hope you like it. It's math. I understand that some people probably reach in the middle and they stop, but at least I think you can take advantage for the 6 use cases that I presented. I think there are good ones that you can apply on your software, even personal life. So I'll let you hear a challenge. If a biased coin is 80% heads, what's the new probability after 2 heads? Just try to apply the formula and check if the result is correct or not. So again, thank you for watching this video. I hope you like it. I will provide probably a more funnier puzzle the next time. I'll put the puzzle every week or something like that when I have time to create these slides. but I hope to see you in all of them. So please subscribe, share it with friends. It's a motivation for me to keep going on these videos. And again, thank you for watching.